Hey folks, welcome to ScienceCept. Today, we have Mr. Astrophysicist to join us and talk about one of the fascinating things about the universe that people want to know, black holes. Though Einstein's theory of relativity influenced further studies that predicted its existence back then in the early 1900s, we are still trying to get the exact picture of the black hole.
So, for our new learners, I would like to ask very first question to our guest, Mr. Astrophysicist, what are black holes?
Hello, thank you for inviting me. So, black holes are the centers of extreme gravitational force, where spacetime fabric deforms such that nothing can escape from it. It is surrounded by a boundary called the event horizon, like what you have shown in this picture. Since black holes cannot be seen as they trap light inside them, sophisticated instruments are used to detect them. Inside a black hole, gravitation force is dominating, so these instruments picture black holes based on gravitational force.
Since black holes have so much power to engulf anything such that nothing can escape out of it, it should have some dependency on mass of the stars.
Black holes are made up of stars. So, they can vary in size depending upon the mass of the star they squeezed in a tiny space. So, basically, they are of two types, stellar and supermassive. Stellar black holes have a mass of more than 20 times the mass of the Sun, while supermassive black holes have a mass of more than 1,000,000 times the mass of the Sun. A supermassive black hole residing at the center of the Milky Way galaxy is called Sagittarius A. It has a mass of about 4 million suns.
It seems so interesting. So, can you elaborate more on the formation of black holes?
Sure, why not? Black holes are born as a result of the death of massive stars. See, it is important to understand the death of stars in order to know how black holes are formed. So, during the lifetime of a normal star, over many billion years, hydrogen fuels the star. But when it runs out of fuel, the internal gravitational force of the star dominates such that it shrinks. Depending upon the mass of the dying star, it could be transformed into either a neutron star or a black hole. This was brought forward by American scientist John Wheeler in his work in the 1950s and 1960s. Adding to this, Robert Oppenheimer in 1939 with George Volkoff and Hartland Snyder showed that a dying star could not be supported by outward pressure such that the star would contract to a single point of infinite density, called singularity.
So, does it mean that every massive star like Sun can become a black hole? And what if Sun becomes a black hole?
See, first thing is, not every star can become a black hole, and secondly, our Sun is not a massive star. Sun is not big enough to become a black hole as it is an average-sized star. But even if Sun becomes a black hole in the future, this miniature black hole would be so small that it would not affect the Earth. Instead, the Earth would keep revolving around the black hole. But life on Earth would shatter due to the absence of sunlight.
Since black holes were born out of dying star, does black holes also die out? I have heard something like Stephen Hawking said they do, but I would like you to elaborate and tell us about the death of black holes.
What I feel is, Stephen Hawking was and will be one of the genius minds who had a significant contribution to the study of the black hole. Yes, you were right that he discovered how a black hole dies. So, in the 1970s, he discovered that black holes can slowly evaporate due to the interaction of event horizon and quantum fields. So, they give off a small amount of energy such that they lose mass. Over time, the black hole shrinks down and ends itself by giving off a flash of light. But this process will take a long time to happen. A black hole will emit only one particle in a span of 1 year. A stellar black hole will take about 1,000 decades to evaporate. The process is called Hawking radiation.
Please tell us more about Hawking radiation.
If you say so. It can be described as black body radiation emitted outside the event horizon such that, if the black hole could not gain the mass by surrounding, Hawking radiation would reduce the mass of the black hole, and eventually, it will die out. It is because, whenever a particle leaves a black hole's event horizon, a small amount of energy is dissipated such that the mass is reduced, as energy is related to mass by energy-mass equivalence. According to the time span described by Stephen Hawking, any black hole formed during the early phase of the Big Bang has lost nearly a petagram of mass till the present day. Hawking radiation seems to lose information about the body as it reduces the mass, and depends on mass, angular momentum, and charge of the black hole. This was suggested by Jacob Bekenstein in 1972. He further suggested that the black hole should have an entropy, degree of disorder of a system of particles. While Bekenstein suggested entropy in black holes, Stephen used the thermodynamic relationship between energy, temperature, and entropy to strengthen Bekenstein's theory. The formula is known as the Bekenstein-Hawking formula, which stated that the entropy of directly proportional to the area of the event horizon. Further studies on the thermodynamics of the black hole led to the development of laws of black hole thermodynamics.
It was indeed an elaborative and nice explanation to the concept. You mentioned that Hawking radiation seems to lose information as the mass reduces. Can you explain more on this phrase? And what is the role of quantum mechanics in Hawking radiation?
Well, Stephen theorized Hawking radiation based on the concept of quantum fields, which says that the empty space is not empty. Empty space has a quantum field having virtual particles.
Virtual particles? What are these particles?
Virtual particles are not particles but the perturbation by the annihilation of particle-antiparticle pair. So, when these virtual particles come near the black hole, some of them may disappear inside a black hole and be lost forever, while some can be emitted as Hawking radiation. So, it is violating the quantum mechanical principle that information should remain intact. And since Hawking radiation is inversely related to temperature, it is thermal radiation, which contains the information of the system. Therefore, it leads to the black hole information paradox. Though Stephen established the fact that black holes can eventually evaporate, the solution to this paradox is still an unsolved problem in physics.
It is indeed a wholesome explanation about black holes. I hope we continue this discussion later on. Alright, thank you so much Mr. Astrophysicist for joining us today.
If you love this video, like and share this video. Subscribe to ScienceCept and don't forget to press the bell icon. Follow us on social media handles for regular content. You can also check out this and other science blogs on our website www.sciencecept.in, link in the description.